today we will study two topics. So first topic will be some statistical problem, and this will cover, if you look at Boyd's book, it will be section 7.1 and 7.5, and this would be page 351 to 359, and this would be 384 to 391. And then we look at classification. And this would be 8.6 pages 422, and I didn't do the last page, so around that page. Okay. So first, do you have any question that you want to ask about class course on duality that you thought about during the weekend, or no? Okay. So first, statistics. So what we will look at is you have a vector x that you want to determine, and what you have is some measurement of x. So x is some unknown you want to know. You have some measurement of x that are linear measurements. So if you have linear measurements of x like that, right? So AI is some vector, and you have, let's say, m measurements, and you want to find x which is an n-dimensional vector. So in that setting, somehow, if you have a few measurements, A1, A2, AM, you can stack them all in some matrix that we will call A. And you can also stack all the y in some matrix. Rather some vector.
Why are the measurements considered A and not Y? Like these are just observed.
So y is what you observe, okay?
Yeah.
You don't know x. You know the AI, and then you observe the y's. Okay, so you don't know what are these x, but somehow you have a few vectors AI that are kind of what the observations are.
So what's an example, a concrete example of what?
So a simple example of that is, let's say, you want to buy bananas and apples, but you don't know what the price of these are, and you want to know what's the price. So first, you ask one friend, can you go and buy one banana and one apple, and tell me what you pay? So your first friend, he go buy, so let's say x1 is the price of banana, x2 is the price of apple. The first friend goes and buys one banana and one apple and told you I pay $3. You still don't know what's the price of bananas and apple. But then you have another friend and you ask him, can you buy 2 bananas and 1 apple? And then he buys 2 bananas and 1 apple. And he says he paid $4.
So A can be thought of as like the quantity and X is the unknown price.
Yes. Okay, so what you decide is, for example, you tell your friend buy 1 banana and 1 apple, or your friend tell you I bought 1 banana, 1 apple. So whatever is the context, you kind of know, you know this matrix A, you know these AIs, and then they tell you basically the price they paid, which is what you observe. Okay, so in that situation, you could guess what's the price of ananas and apple. You can see, okay, apple are $2 per apple and $1 per banana, which is quite expensive. But if your second friend bought like 2 apples and 2 bananas, it wouldn't have been very helpful, because then it would have been, of course, the same information, right? But if the rank of A is rank n, you can actually get the information. So this you know, this is solving linear systems. What we look at here is a situation where you have some noise, Vi, on each measurement. And so because of that, you cannot really solve this linear system. What you have instead you have that y equals ax plus v, the vector of noise. So what will you do in that case? What do you think? Yes?
Maybe you find the x to minimize the magnitude of v.
Okay. Yeah, you could do that. So you're telling me you minimize. So what do you mean by the magnitude of v? V is a vector.
I guess sum of squares of each component.
Okay. So the 2 norm of v. Very good. What else could you do?
So V is like a known noise model, like you know the distribution.
Good question. So suppose indeed that you know the distribution of v.
Okay, so can't you just solve it in expectation?
Mm-hmm.
Just use the mean?
Yeah, you could use the statistics. So let's assume v as mean 0.
You could do like a worst case or something, or like the actually we can't.
So somehow you can get the v. So from that you have that v is actually y minus ax. So instead of saying I observe some y's and I don't know x, somehow in the optimization problem you're trying to find x, and for each value of x you can actually find the v that corresponds to this value of x. Okay? So in the context where you have decided some value of x, you can see this as you're actually just observing some v. So you have some statistical model, some density function for this vector v, and you are observing some v. And so in that case, what you can do it's what is called a maximum likelihood estimator. So basically, once you observe this v, you can look at what was the probability that this random variable v would be equal to what I observe, which is y minus ax. And what you can do is you want to find the x such that this probability is what? Minimized or maximized? Yes. Okay, so somehow if you have a statistical model on V, you could try to say, let's find the x that maximizes this quantity. And somehow the x such that what I observe is the most likely is probably the best x. And so to simplify, if we suppose that v, so the vector v, which has dimension n, so it's v1, vm. If we suppose that they are IID, so independent and identically distributed, it means that, how can we simplify this if they are independent, the VI? Yes?
Multiply?
Yes. So this becomes, so the product of the probability that V1 equals Y1 minus A1 transpose X times the probability that Vm equals Ym minus Am transpose X. Very good. Okay, so now we can maybe assume, so what we do for the rest depends on kind of what's the distribution of each VI. So if we assume, for instance, that VI is some normal of mean 0 and say variance sigma, what does this become? So we need to try to remember what the density function of this. So it means the density of VI is right? So if we plug this in, we get maximum of, so we have 1 over 2 square root of 2 pi sigma. This is a constant, so it appears in all of these expressions. And then you have exponential of minus What can you do now? To go further. Yes?
You can combine the exponential so that it's a plus.
Yeah, very good. So this can go out, it's a constant. So you have the exponential of, and then you have minus y1 minus a1 transpose x squared. Okay. Now what? Can we somehow get rid of this exponential? If we maximize the exponential or something, it means that what are we doing with what's inside? We maximize or we minimize? Why? Exactly. So the exponential, it's monotonically increasing. And so this is the same as, so this we can forget. If we're just looking at what's the, somehow the maximal x, we can just care about what's here. So it's minus, and in fact, we can see that it's the 2 norm okay. Or alternatively, we can say we minimize and get rid of the minus. Okay, so surprisingly, in fact, what we get here is exactly the idea we had from the beginning. So somehow this ID was assuming IID normals for VI. So this regularly shows that if we assume IID normals for VI, in fact, this is what we should do. But then we can look at what happens for other probabilities. So normally when you do, so that's shortened MLE. When you do MLE, what you like to do is, instead of products, usually products are kind of nasty, we like to take log likelihood. And so when we take log likelihood, instead of this, we get maximum of the sum of log of probability Vi equals again, because the logarithm function is increasing, we can apply, instead of maximizing this, we can maximize the logarithm of this. It doesn't matter. It will get you the same x. Now, if we do that, would that change anything to what we did?
No, isn't it just skipping that step?
Yeah. So instead of removing an exponential at the end, we would have just added a logarithm at the beginning, but it's exactly the same. Okay. Okay, so let's take another example. Let's assume now that the VI, they are again IID, but now the distribution is different. We assume that each vi is Laplacian, which means 0, and parameter b. So it means vi Okay, so if we start from here, there is an absolute value here. Okay, so assume you know this parameter b, right? You're just looking for x. Okay, so in that case, what would we get? Yes?
Does this ultimately become the one norm?
Yes, exactly. So here, this is constant, so we don't really care. This also goes out. Somehow you have minus log of 2b of minus 1 over b times the minimum over x of okay, and this is denoted as the one norm of v. Right? Because by definition, the p norm of v is defined as the sum okay, so in this case, we had the two norms squared because each term was squared. And in this case, each term is to the power of 1, and so this is the one norm. Okay, so in fact, here, when you say I should minimize the magnitude of v, what does it mean? It's a vector, so it's not clear which vector is smaller than which one. So you should have some way to scalarize it. So the way you scalarize this v and make it clear for the optimizer what do you mean by the smallest v actually depends on what is the noise model you have for the vi. If you have a Gaussian noise model, you should use the 2 norm. If you use a Laplacian noise model, you should use the 1 norm. And then let's take a last example. What happens if you Yes?
So how can we see that from the we have right now?
From the one norm or from the Laplacian?
Yeah, I mean, is there any intuition related to this?
So why do you say this encourage sparsity? Because you know Laplacian would encourage, or because you know the one norm would encourage?
Oh, yeah, I'm asking, yeah.
You know that the one norm encourages sparsity, so you're wondering why?
Yeah, just if there's any intuition.
Yeah. So if you look at the density function of Laplacian versus the Gaussian, you kind of have it's like you're looking at which distribution has the longest tail. So somehow if one distribution has a longer tail, versus one distribution which has a much shorter tail, let me do a better drawing.
The tail is just like the hole that
So the one would be like that, and the other one would be probably like this. Which distribution for the noise would encourage sparsity? Like just in terms of tails, not in terms.
So one that's small tail.
Small tail. Mm-hmm. So with this one, it's like, it's very likely to have anything closer than 0. It doesn't really, and it's very unlikely to have something far from 0. And in this one, it's like you might have very, very large value. This can be very likely, as well as very small values. So that's in the intuition in terms of the noise. And then in terms of the 1 norm versus 2 norm, you can see that in the 2 norm, it penalizes a lot large values. Because it's like, suppose you have two, this is like looking at the mean. So if you have two values like 10 and 30, their mean is 20. If you have 20 and 20, their mean is 20. But then if you take the squares, here you will have 100 plus 900, which will be 1,000. And here you will have 4,000, which will be 800. So somehow with the 2 norm, you penalize more the big values. While in the 1 norm, you penalize less. It's like if you have 1 small and 1 big, it's kind of the same as 2 medium 1. So the fact that you penalize more the big values for the 2 norm is kind of the same as having a very short tail. Because having a short tail means it's very, very unlikely that you have very big values. And so whenever you have a big value, you will put a big penalty. And so in the sparsity, you're like, I don't want to put a big penalty on large value. It's just I want to put a penalty on non-zero value, that's it. So it's like if you have a very large value or a very small value, I don't care. I just want 0 values. And so in that sense, the ones who has a very long tail would encourage sparsity. And would be the 1 norm. And the one who has a very short tail would be more like the 2 norm and would less encourage sparsity. Yes?
I mean, 2 norm would encourage sparsity, right? Because it would force everything to be closer to 0.
No, so the 1 norm encourages sparsity more than the 2 norm, I assume.
Oh, really?
Because in a sense, so the real, so the norm that is the closest to encouraging sparsity is the 0 norm, if you want. It's like if you take the limit of p to 0, then it's like if you take p to 0, it's not going to be very well defined, but it's like you want to take 1 if Vi is non-zero and 0 otherwise, and take the sum. So in a sense, it would be a function that is, if Vi is 0, then it should be 0, and whenever you leave, it should be 1, and then it should just be constant. So in a sense, you shouldn't penalize more big values than small values. And the more you increase p, the further you are from this. So that's why we say that the 1 norm encourages sparsity more than the 2 norms. And if you take the 4 norm or the 6 norm, it's even worse.
By sparsity, do you mean close to 0 or exactly 0?
No, sparsity is you want to minimize the number of non-zero. So it means that if you have 0, 0, 1 billion compared to 0, 1, 1. So for the 2 norm, this is very bad. But for the sparsity norm, this is the best one. Like if you want a better example, you can say 10, 10. And this would be so for the 1 norm, this one is better, because this is 15 and this is 20. So for the 1 norm, this one is better. But for the 2 norm, this would be square root of 100. And this would be square root of, what's the square of 15? 225, or am I think it's correct. So for the 2 norm, this one is better. And for the 1 norm, this one is better. And for the sparsity, this one is better. So sparsity actually is closer to, 1 norm is closer to sparsity. And so long tail, yeah, is also better. Okay. So the last example, no, I need to erase that. Like if you wanted to do the distribution for the sparsity, if you want, it should be something like, so at 0, it's very likely that you are 0. And then non-zero, it's very unlikely. Something like that. So this would be some epsilon. And this would be, again, some very small epsilon. And then you would take this epsilon to 0. So at some point, you would converge to the Dirac measure if you want. That would be the ideal sparsity penalty. So you see it has an infinitely long tail. So now suppose Vi IID, and they are uniform from minus A to A, which means that basically you expect the noise to be something from minus A to A. Any noise in that interval is as likely, but a noise outside of this interval is completely unlikely. So in that case, when you take, in fact, any of the formula, what's going to happen is that if yi minus ai transpose x is outside the interval, you will get a probability of 0. And whenever it's inside the interval, you will have a probability of 1 over 2a. So the probability of
These distributions always have to be like symmetric.
it doesn't have to, but usually when you talk about noise in that kind of situation, in that context, it makes sense that they are centered as 0. Because if you don't have 0 noise, it's more complicated to make your measurements. So yeah. But you can have contexts where they are not symmetric, but then if you know what is the mean, you will just shift by this mean. Are we going with time? So in that case, this would be 0 if is not in the interval, and it will be 1 over 2a otherwise. And so in fact, in this case, it will actually ask that the infinity norm is smaller than a. In fact, a is a bad choice of variable because we already have a, let's say, alpha. And so with the uniform distribution, you actually have the infinity norm, which is even worse for sparsity. Okay? So now what about map estimator? So for these estimators, what happens is that you have some prior knowledge on X. So in fact, if you really look at what you are doing, you are observing some Y, and then you are trying to infer what is the most likely X, given that you have observed these Ys. And so in fact, what you should maximize is the probability that the random variable x is equal to x if you observed y, which is denoted as p y if x y if x. This is conditional probability, so this is exactly this. It's a notation for this. You know Bayes' formula? Any one of you know Bayes' formula in statistics?
Okay, like the base rule?
Ah, yes. Yeah, I have a bad way to pronounce things because I've seen this concept in French. Yeah, the base rules. Okay, so the base rule says that, like, basically there is two ways to compute the probability of observing x and y. So the first way is, say, I first observe x, and then I multiply by what's the probability of observing y given that I have observed x, or I first observe y, and then I look at the probability to observe the given x given that I've already observed some y. Okay? And it's two ways to look at the same quantity, so in fact they are both equal. And so here the quantity we are looking for is this one. And so in fact we can isolate it, and we see that it's equal to okay, so given this, here because we are maximizing over x, we don't really care about this part because it's constant, so we can move it out. And so, and we can do the logarithm trick, and we can say we maximize over x the logarithm of p y given x. Okay, and in fact, if you look at what we did before, this was exactly what we did here. Is here we maximize which probability? When we did the MLE. Yes. So when you're doing MLE, what you're doing is assuming that this is constant over x. Okay? In fact, most of the time, this is not constant over x. It's maybe uniform, and you still have some domain for x. So if you have some domain for x in this case, you can add the domain as constraint of the optimization problem. So in this case, if you have some linear constraint over x, what does the problem becomes? So you want to maximize over x, y minus ax. And maybe you have that the xi are between -1 and 1. And maybe you know that the sum of the xi is smaller than 10, things like that. From which class this problem belongs to? Is it convex? Yes? You need to minimize. Otherwise, it's not. Is it a linear program? No. What is it? Yes? Yes, so it's a QP, quadratic program, because it's a quadratic objective, but all the constraints are linear. Now, if I use the one norm, what would it be? Yeah. Linear, yeah, because you can express the one norm as linear. If you use the infinity norm, this. So for the infinity norm, you have that basically yi minus ai transpose x smaller than alpha. How can you model that? And then, so this is equivalent to this for all I, which as well as and these are two linear constraints, okay? So the infinity norm is just, you can express it as m linear constraints, 2m linear constraints. Okay, so infinity norm is also linear. Okay, so one norm and infinity norm, you can always express them as linear constraints. All right, so in this case, depending on, because at the end of the day here what we did is kind of looking at the probability of V. Here we can play the same game with the probability of X. If we assume uniform probability of X, we will get here a infinity norm. If you assume Laplacian probability for X, you will have one norm of X. If you assume Gaussian, you will have two norms for X, and so on. So for example, if you say X is normal of mean X bar and covariance matrix sigma, what you will have here is that one over, I mean, this is just constant, like the only non-constant part is, so something here, exponential, something here, and here x transpose sigma x. Minus x bar. X minus x bar. And so what this becomes is so if you assume for x, if you assume a Gaussian distribution, so it means you don't know x, but you know that if you had no information on x, you just know it has this distribution. And then some x is picked from this distribution, and then you have additionally some measurements y. And so what you do is when you look for x, you take into account the measurements, but also the prior information you add on x. And if this prior information was that x followed this normal with this sigma, then what you would get is this expression where sigma is a positive definite matrix. So in the case where you assume that x is 0 with the identity, then here what you would simply have is the 2 norm. Yeah, put it here. Here you have the 2 norm of x. But in the more general case, you have that. So this, if I have this in my objective, and suppose the rest is linear, what is the class of program I have? Yeah, again, it's quadratic because this is quadratic in x. Okay? Okay, good. So
So what's an example of like a clear case when you want to do MAP versus
so whenever you have any prior information on x, you should always do.
Remember to repeat the question.
Oh, yeah, sorry. So the question is, when should I use MAP and when should I use MAD? So somehow you should always use MAP. It's always better somehow. But sometimes you have no information on x, no prior information on x. And so if you have no prior information on x, it's like if px is constant, like any x is as likely because you have no information on x. And so MAP, just in that case, it just reduces to MAD. So somehow you should always use MAP, but in the simple case, when you have no information on x, you could say I'm using MAP, but you could as well say I'm using MAD just to simplify, because MAP is just a generalization of MAD. Is that answering the question?
I see. So basically, if your inputs are kind of like a simple data type where you actually have a good like analytical distribution, then you can maybe get some more power from MAP.
Yeah, it's always more accurate, yes.
Like I guess like computer vision and all these high dimensional things, it makes no sense, right? Like if you're taking an image as x,
Mm-hmm.
you don't have any expression for px or x. Maybe you could train like a
Well, what you know is that probably what you would say is that my image is some uniform from 0 to 255. So the only information is that it's a valid pixel.
if it's uniform, then it reduces MLE. Right?
Yes, exactly.
Okay.
Mm-hmm. But you could say, for instance, it's more likely that the pixels next to each other have not don't vary like abruptly. Like your image is not a noise; it's actually a nice image that represents something. So most probably, most pixels next to each other are very close. So that could be some prior you could use and use MAP to be more accurate than MAD. So the code for the participation survey for people online is design. Okay, so now suppose we go back to the MAD. So we have yi equals AI transpose x plus vi. And we will assume vi are IID normals. Okay, so we know that we should solve this problem, this square problem. So this problem, if you have some constraint on x, like for example, you know x are some pixels, so you know 0 is smaller than x, smaller than 255. This is a QP, right? But suppose you have no constraint on x at all. You just solve the unconstrained minimization of this norm. In that case, it's just minimizing a quadratic function. We can all do this, right? So you want to minimize x transpose ax plus y transpose y minus 2 So how do you get the minimal of this function? You just derive by x. If you get the gradient by x and you say this is 0, you have A transpose AX and so you have that x is and so if you look at the error that you are doing with the true value of x, so this would be your estimate that you compute. If you look at the difference of the two, then if here you substitute y for its value, so you know that y is ax plus vi. So this is ax plus v. And so here you have some cancellation. You have this becomes x plus so in fact, this is what you should have. This is the value you're looking for, the true x. And what you have estimated is this. So this is the error that you are making. So if you look at the error, what you have estimated versus what you wanted to get, it's exactly this. And so because of this, you can get an estimate of the covariance of the error. So if you look at the expectation of VV transpose of x minus x, if you look at the covariance of the error, what you have is so here, because A transpose A is a symmetric matrix, this transpose doesn't really matter. So in this case, because we assume that it's a normal N01, this means that what is this? No. So if we look at the expectation of Vi, Vj, for I different from j, what is this? Yeah, exactly. So for of diagonal entry, it's 0 because they are independent. And then it's 1 for I equals j because the variance is 1. So it's the identity. So very nice. This becomes the identity. And so A transpose A cancel with this one, for instance. And so you have yes?
So in the derivation, what's the difference between x hat and x?
So x is the true value of x you don't know. And x hat is what you obtain by solving the least square. So you have the value of y, but you don't know the value of x. So you have the value of y, which is ax plus the noise. Okay, so you have the value of y, you know it, which is ax plus the noise. And then from the value of y, you get your estimate of x, which is you take y and you multiply by this. Because this is the solution of the least square. Okay, so x hat is the solution of the so arg mean of this is x hat. Okay, and x in here is the true value. It's a bit confusing because here this x is not really the true value. We might have chosen a different.
Wait, so does the flat and the triangle with the wedge mean the same thing? Did you just
Oh, where is the flat one?
like you wrote it with a line on top?
Ah, yeah, sorry. Okay.
The final thing that you did was you showed us the expectation of the covariance of the error.
Yes.
And you say there's a simple expression A transpose A.
Yes.
And the noise model is standard Gaussian.
Yes. So this means that if you know the noise is like that, but you want to choose what are the AI, then you can actually choose the AI. For example, in the example where you could choose, like you have your friends, you can say you go buy 1 banana, 1 apple, you go buy 2 banana, 1 apple, and so on. Like what you ask your friends to buy. If you know that they will exactly tell you the price, it's fine. But if you know that your friends would forget the price and give you some error on the actual price they paid at the end, then if you know there is some noise, there might be some optimal thing you should tell your friends. Maybe saying the first friend buy 1 banana and the banana, there is no 1 banana, and the second friend buy 1 apple. Maybe this is not the optimal choice because of the noise. Okay, and if you want to get the optimal choice, what you need to do is you need to take this covariance matrix to be as small as you want, because that means that the error is as small as possible. Okay, and then you have a new optimization problem, which is trying to get the minimal covariance matrix. So find the AI which gives you the minimal covariance matrix. Okay, I won't go further into details for this, although I won't have time for the last topic. But you can have more information in these pages. So it's 7.5. These pages explain you how to choose this AI. Okay. So last topic would be classification. So it may look a bit similar. We again have the same equations, but it's not the same really. So you have some cloud of points. And what you want to do is you want to find a classifier. So basically, someone gave you these points, and they said this point should belong to the first group, and these points should belong to the second group. Okay? So maybe I should have said this, the cross should be in the second group. And so you have this labeled example. From this labeled example, you may infer that this is a very good classifier. And so whenever you have a new example, you can look, is it on the left or on the right of this hyperplane? And depending on that, you can know whether this should be a cross or a circle. Yes?
Does it always have to be to some classification, or can you pick like the order of the classification? Like for example, if you have like 4 groups, multi, I guess, classifying it by more than just as your classifier.
Yes, but here we only focus on just 2 groups. Okay, so because there is only 2 groups, you can, you hope to be able to classify with just one hyperplane. So first, suppose that they are linearly separable, so there exists some hyperplane that separates both of them. The question is, how do you find this hyperplane? So suppose these points, it's x1, x2, x3, and so on, and this point are y1, y2, y3, and so on. So this hyperplane, you might characterize it as A transpose x smaller than b. So these sides are the points such that you have this, and the other sides are the points such that A transpose x is larger than b. So it means that to find this hyperplane, you want to find somehow this vector A and this value B, such that you have okay, so this is a linear problem. You want to find this A and B that satisfy these constraints. No, the problem is that these are strict inequality. We don't like strict inequality. And also, there are many different solutions. Like, you might have these solutions as well. Like, how do you know which solution is the best one?
Does it matter if it's strict inequality? Like, isn't it common for people to just interchangeably switch between strict?
Yeah, you could. This is not the biggest of the issues. Sorry. So the question is it really a big issue that we have strict inequality? Can we just somehow by continuity just say, let's use non-strict? Indeed, it's not that much of an issue if you think it like that. But somehow it's apparent of another issue is that when we say we want a strict inequality, what we mean is in fact that we would like to say it's much better to have like this one where you have a big distance with each node rather than this one which is even touching the nodes and you have absolutely no slack and no margin. So how do you say that, how do you somehow make sure that you have the best margin possible. Yeah.
I guess you can introduce like an epsilon, so less than or equal to b minus epsilon, greater than or equal to b plus epsilon.
Okay.
And include that in as a maximizer.
Like that.
Or I guess like you'll be minimizing negative epsilon, I guess, because we want to make epsilon big. Okay. Yeah.
Okay.
And then we can do less than or equal to and greater than or equal to any constraints.
Yeah. Would that work? What do you think?
I guess unless epsilon is 0.
Wait, so epsilon has to be like positive.
So if you have like if you're able to have a big slack, it means you can use like if you take an epsilon that is positive, it's not helping you making this satisfy. So being able to take a big positive epsilon means you have big slack, right? So indeed, so if you find a positive epsilon, it means they were indeed separable. If you find a negative epsilon, it means this set of points were not separable. And this value of epsilon kind of give you an idea of how much they were separable or not. But in fact, there is an issue in that formulation, in the sense that this formulation is homogeneous, in the sense that if you give me any solution, so if you give me any solution A, B, epsilon, then I can take the solution 2A, 2B, 2 epsilon. So somehow multiplying a solution by any constant doesn't change anything to the feasibility, but then it changes the objective. You see, so it's not going to be, if you have A1, B 0.001, and then you have A2, B2, 10, you want to say this one is much better than this one. But then from this one I can take, from this one you have the solution 1 million A, 1 million B, 1000, which is exactly the same solution. It defines, this one defines the same hyperplane. This one and this one define exactly the same hyperplane. I just multiplied A and B by the same number. But then suddenly this solution becomes very good because epsilon is 1000. And here it seemed that this one was better. And so now this one can say, oh, I do the same. I multiply myself by 1 million or 1 billion, and then, yeah. Yes?
I guess so maybe to fix it, you can take the ratio of epsilon to magnitude of A, or we can add a constraint on the size of A and B.
OK, we could divide by the magnitude of A. Then we don't like it because it becomes kind of not so linear. So yeah, we could as well take a constraint. But what's the, like it seems like kind of hacks and heuristics. What's the thing that somehow is hiding behind that? What is the step that we did too quickly? What is the thing we want to represent here? What should epsilon kind of represent geometrically here?
Like the projection to the
OK, so if we have this point, this projection is this point. And what does epsilon represent? Yeah. So geometrically is what? Distance, exactly. So we want to represent the distance to an hyperplane. So if you have a point x and an hyperplane A transpose x smaller than b, let's say, what's the formula of the distance of this to the hyperplane? You should indeed take A transpose X minus B, you should indeed take the two norm. But then you should, in fact, also divide by indeed the norm of A. Right? And so somehow, in here, because you let the norm of A become anything, epsilon doesn't really represent the distance. So what you really want to do is say the norm of A is equal to 1. Would it be a good idea to add this constraint or not? Yeah, exactly. So the formulation seems to correctly represent, like we would get the solution we want. But then the issue is that problem convex? Yes. Is it convex? No, because if you take a quadratic function and you say what are all the points that are equal to something, I have two separate points. So if you look at this set of two discrete points, it's not a convex set. Yeah.
So maybe you can do less than or equal to 1, but you can prove that it should lie on a boundary. If it doesn't scale up, it's not lying on a boundary.
Exactly. So if you take the two norm of A smaller than 1, no, the prime is convex, but no, it's convex, but is it still what we want? Because no, the problem, like the solver may give us a value of A which has not norm 1, and so it means that epsilon would not represent the norm. Except that we have seen that the solver will always want to scale up epsilon, because it's always a better objective, and when it scales up epsilon, it scales up A. So the solver will always prefer large norm for A. And so if you just say the norm of A should not exceed 1, the solver will still always give you A with the norm 1, because if it finds something with norm A smaller than 1, it will never be optimal, because you can just scale it up like this. So this is very, very often when you do convex formulations, you will need to reformulate equalities into inequalities like that. And what you always should do is think, OK, is this equivalent that I'm using an inequality rather than an inequality? And you will always need to do this kind of reasoning. Yes, it's equivalent because if the solver finds a solution for which you don't have equality and you have strict inequality, this solution will never be optimal because it can always be improved by, for example, multiplying the solution by whatever. So this is very, very, very common thing you should do. All right, I believe time is almost up. So one last thing I want to mention about this. Sometimes you might be in a situation where for example, a situation like this. So would our approach work very well in that situation or not? Or would that completely fail? It will not work very well because this is clearly not linearly separable. So you will not be able to find a hyperplane. What we would like to do is take this to separate, but this is not a hyperplane. So what can we do? Instead of looking for A transpose X smaller than B, which would be an hyperplane, we want to look for A1 X1 maybe. That was the initial. Like this would be an hyperplane, but then we can also say maybe A3 X1 X2, or maybe A4 x1 square, or a5 exponential of x1. Like you can add these terms, but these terms are not are nonlinear. This term is not convex in X. So how can we get a convex formulations if you want to use these classifiers with these nonlinear or even non-convex terms?
Some arbitrary polynomial function.
Yeah, or even exponential or cosinus or sinus of x. Is it possible to still solve a convex program with that? It's also a very important thing that will appear a lot when you do convex formulations. You will see these things and you will say, oh no, this is not convex, there is no hope. Or is there? Like this is when I say this is non-convex, it's not convex in X, right? And X is basically one of the points that you have here. So for each point, you will have some values of X, and then you can evaluate each of these. But at the end of the day, what you want to find is A and B. And this is not convex in X. So for example, for this point, this coordinate is maybe -3, -2. And so for this point, when I evaluate, exponential of -3 is something. Here I have a4 times 9 plus a3 times 6 plus a1 times -3 plus a2 times -2 smaller than b. If you look at this, is it still something that looks non-convex, non-linear, or does it look like an hyperplane? This is just some number, some number, some number, and this is just linear in A. Okay? So the x is just a constant in this. So when you give this to a solver, it doesn't see the nonlinearity in x. For him, x is just a constant. So in fact, you can have some sum of ai phi I of x, j sum of ai phi I of y j. And this phi can be any functions. You can have phi of x be some polynomial in x, some trigonometrics in x, some exponential in x, whatever, because these, when you give this to the solver, this will be just values, numbers, floating point numbers. And the solver will just try to find the ai and the b and the epsilon. And so whatever is the values you choose there, you will just have linear constraints. Okay? So when you do convex formulation, when it's only convex in the decision variables, you don't care about nonlinearities in the data. Okay? Yes?
I guess just to confirm, the specific form of the function, you would still have to hard code in, right?
Yeah. So you need to decide some phi. It will not try to find the phi for you. You decide some phi from your intuition or whatever, and then it will. If you pick a phi that is not useful, then it will just put ai, which is 0 for this phi. So somehow this is a convex problem. So this will be solved to optimality very efficiently. So you can put many phi. There is no problem with that. And it will just pick the phi that works good for you. This is what this method works very well in practice.
I forgot if it was the right name, but is this stuff related to like SVM SVMs? And
Yeah,
then
this is
kernel?
this is yeah, this is the SVM support vector machine. Yeah.
Okay, so you introduced SVM, and then the thing you just introduced is called the kernel trick, right?
Yeah, exactly. I mean, this is just the basis vector. The kernel trick is yeah. I didn't go to this, but yeah.
So does anything change when you have like K-way classification? Like, not, this is just still binary classification.
Yeah, this is just binary classification. Yeah.
But it still works, right? If you have multiple groups of labels.
I think it starts to be probably more complicated.
In the SVM for multi-class, you're always doing one versus all classification.
Yeah.
Can you repeat that answer?
So the question is, what happens if you have multiple way classification? And the answer was, in SVM, you always classify one group against all other groups.
So is there like some intuition for why it's hard to do it like simultaneously? Because maybe you can, yeah, I don't know. It seems like it might be possible to formulate some geometry per group or something. Oh, I guess it makes sense. I see. We can't get like a bounded
Mm-hmm.
shape. Is that why it's 1 versus k all the time? Or 1 versus k minus 1? Just because you can't get a bounded shape, it's not simple to.
Yeah. So yeah, the question is, what's the intuition behind the fact that we can only somehow classify one group from another one? And I guess the intuition is that the trick here is really you try to find some functions and you can see this, and then you will take some level of that function, which is b, and then you will look at what's the level set of that function. So what are the value for which this function is lower than this value? The x such that this function is lower or higher than this value, and this naturally gives you two sides.
So like why is when you want to do this versus the neural network stuff everybody's doing? When is this more powerful or better?
It's a lot easier to calculate.
So the question is, when should you do SVM versus when should you do neural networks? I guess I'm not experienced enough in machine learning to give you experience advice, but I guess you could try both.
Like, do you think there's any inherent limits to the expressivity of this formulation in terms of like high-dimensional problems?
What?
Is it inherently like limited in terms of how expressive the features you can use are, or maybe I guess the decision boundary? Is there like some inherent lack of capacity in
So
how complicated your decision boundary can be?
the question is there some fundamental fundamental blocking things for the expressibility of this approach? I guess the big difference is that somehow here you want to, so you can choose arbitrary nonlinear functions that can be arbitrarily complicated, but then you just combine them linearly, right? And it's like if you have, maybe it's far-fetched, but it's like if you have one layer neural network with very complicated function for this layer. And for neural networks, you would rather take very simple nonlinear function, but then many layers.
Oh, so there's no depth kind of
Yeah.
thing happening here. There's no hierarchical thing happening.
Yes.
In terms of how you can model.
Yeah. So when here you decide to take, you here need to decide to take like combination of different things, while in the neural networks, because of the network structure, you have exponentially many combination of all the neurons, and it's going to go through all of them and try to find the best weight. And by combining very simple nonlinear functions, you will have high expressibility. While here, you need to list to give a list of all the nonlinear functions, and they will not combine into each other. They will just combine linearly. No.
Why not make the phi a neural network? Does that not make any sense?
The question is that
Features.
the question why don't we combine them? The answer is that here we want a convex problem.
You just can't optimize it.
Yeah. So the advantage here is that because these things are linear, we can solve it very efficiently. And because we can solve it very efficiently, you can have a lot of phis if you want.
If you were to make phi a neural network, this is the problem that you solve to train the last layer of your neural network.
Yeah.
Right. Once you've already trained everything, this could be a classifier at the end.
So you can do it. Maybe that helps a little bit to set it up that way.
Yes. There's. We can talk after